Today we'll have a look at chemical energetics, but before we get into that, let's have a look at our periodic table of the elements. Now, as you can remember from previous chapters, we know that each element has a different number of electrons in its shells. Now, the important part of the electrons is the electrons in the outer shell. Now, we know that a hydrogen has 1, beryllium has 2, and as we go on, they increase until we get to our noble gases, which has 8 electrons in this shell. Now, we know already that all of these atoms would want to be like our noble gases. They want to have 8 electrons in their outer shell to become stable, and this is why elements react with one another. Now, chemical energetics as a topic has to do with the energy exchange between the atoms. So remember, when a chemical reaction happens, bonds will break and then rearrange and form new bonds to form new molecules. Now, all reactions will transfer energy in some form. This could be either heat, like in combustion reactions, and this is the form that we would work with most of the time. It can also be light, like photochemical reactions, sound, like explosions, or even electricity. The transfer of energy can happen in 2 directions. The first is to the system, meaning to the reacting chemicals. This means that the reaction will feel cold because it's pulling heat away from the surroundings. Then the second is to the surroundings. So this is towards anything other than the chemicals itself. This will mean that if you touch the reaction, it will feel warm because it's losing energy to its environment. Now, the energy that's being transferred comes from the bonds between the atoms, either breaking or forming. But we will get into more detail about this just now when we explain the difference between exothermic and endothermic reactions. So the first type of reaction that we're going to look at in a little bit more detail is exothermic reactions. Now, an exothermic reaction, the reaction system gives off energy. So the thermal energy will be transferred from the system to the surroundings. This means that the system loses energy because the system is giving away energy to the environment. And that means that the energy change will be negative for this reaction. Now, because the system is giving energy to the surroundings, it means that the temperature of the surroundings will increase because the surroundings gain energy. Now, we can visualize an exothermic reaction by using a reaction pathway diagram. So in this diagram, it would be a graph that's energy plotted over the progress of the reaction. So the first part of the graph will show us the energy of our reactants. And we can see that here the reactants has quite a lot of energy. Then we also have the energy of our products. Now we can see here that the energy of our product is much lower than the energy of our reactants, showing us that our reaction would need to lose energy to be an exothermic reaction. But of course, our graph isn't just going to be able to go straight down from the energy of reactants to the energy of the product. The graph would first go upwards, so increasing the amount of energy needed, and then decrease to the energy of the product. Now, this little bump of energy is called the activation energy, and it's the energy that's needed to make the reaction happen. It's the amount of energy that's needed to initiate the reaction. We then have a second value that we need to know now, and that is the difference between the energy of the reactants and the energy of the products. And this is the amount of energy that is released by our system or gained by the environment. Let's have a look at some examples. So the first real-life application of an exothermic reaction is combustion. And combustion is a reaction in which a substance will react with oxygen, then releasing energy as heat and or light. Now, these include things like wood burning. It could also be petrol burning, and then, of course, like the combustion of butane in lighters. The second example of an exothermic reaction is oxidation, and oxidation includes rusting of iron. This is a reaction where an atom or a group of atoms lose electrons during the reaction, so they lose energy. Another good example is the spoiling of fruit. Here, oil in the fruit reacts with air, releasing energy. Then the last type of reaction that I'm going to go through is neutralization. And this is a reaction where an acid and a base react to produce a salt and water. So example is, for instance, the formation of sodium chloride or table salt from hydrochloric acid and sodium hydroxide in the lab. Also, the anti-venom for wasp stings. So the venom from a wasp would be a base, and the treatment or the injection that they would give you is an acid. Then, of course, lastly, we also have antacids, which is also an example of a neutralization reaction. So, antacid is a base that would counteract the acids in your stomach. Now we can have a look at endothermic reactions. Now, endothermic reactions are much less common than exothermic reactions, and they are much less exciting than exothermic reactions as well. Now, in an endothermic reaction, the thermal energy is transferred from the surroundings to the system, which means that the system gains energy. This means that the change of energy in this example will be positive and not negative, such as in exothermic reactions. Now, the temperature of the surroundings will decrease because the surroundings is losing energy to the system. So remember not to get confused between endothermic and exothermic reactions. In exothermic reactions, the system loses energy, and in endothermic, the system gains energy. But because the system is gaining energy, it is taking away energy or heat from the surroundings, and it will actually feel cold to the touch. Just like in exothermic reactions, we can also visualize endothermic reactions using a reaction pathway diagram. So first we'll have a look at the energy of the reactants. Now here we can see the energy of the reactants are very low, meaning that they're very low on the y-axis of the energy progress of the reaction graph. We can then have a look at the energy of our products. And the energy of our products are much more than the energy of our reactants. So it's going to be much higher up the reaction pathway diagram graph. Now, just like in exothermic reactions, our graph won't increase straight from the energy of the reactants to the energy of the products. It will increase the energy above the energy of the products and then decrease again to meet the level of energy of the products. So here, our activation energy will be the difference in energy from the energy of our reactants all the way up to the maximum amount of energy needed for the reaction to take place. And then, of course, we also need to know the difference between the energy of our reactants and the energy of our products. And this will be, in this case, positive, as our reaction is gaining energy. Okay, so let's look at some real-life applications of endothermic reactions. So the first example is the recharging of a battery, and car batteries are a good example of this. Other examples include like the production of chloride gas from sodium chloride being electrolyzed. Now, both the recharging of a battery and the production of chloride gas is an example of electrolysis. Now, electrolysis is a reaction in which electric current is passed through a substance to cause either oxidation or reduction. Another example can include like the electroplating of metals that's often used in jewelry. Then another example is thermal decomposition. And in this reaction, it is where a compound is broken down into two or more products while being heated. An example of this is in baking. So baking soda will decompose into carbon dioxide, making the bread rise. Lastly, the first stages of photosynthesis is also an example of an endothermic reaction. So in these stages, light energy is absorbed by the reaction for the process to take place.